Modern engineering secrets were hiding in ancient documents for centuries. Across 30 forgotten blueprints, you will discover how visionaries from the distant past predicted our technological world with shocking accuracy. We will explore mechanical computers built 2,000 years ago, Renaissance designs for flying machines, and automated systems that feel impossibly modern. This journey will reveal why these revolutionary ideas vanished from history and how they perfectly align with principles used by engineers today. You will gain a completely new perspective on human innovation, seeing our technological story not as a straight line but as a spiral where genius emerges, disappears, and is reborn. How many of today's breakthroughs were already imagined by minds from forgotten eras? History itself became the greatest obstacle to these engineering revelations. Political collapses erased entire libraries of knowledge in moments. The legendary burning of the Library of Alexandria was not just a loss of scrolls, it was the deletion of countless minds, a catastrophic reset button pressed on human progress. Empires crumbled, taking their technical secrets with them into the dust. During certain eras, unconventional ideas were actively suppressed, their creators silenced or their work labeled as dangerous heresy. But sometimes the loss was quieter, more tragic. A design could be so far ahead of its contemporary technology, so lacking in the materials or manufacturing techniques needed to build it, that it was simply filed away and forgotten, dismissed as an inventor's beautiful but impossible dream. This pattern of loss and rediscovery reveals a startling truth about innovation. It is not a steady, upward climb. It is a fragile flame passed from one age to the next, often guttering in the winds of upheaval only to be rekindled centuries later. With this understanding of how easily genius can vanish, we are ready to encounter our first forgotten blueprint, a device so advanced it would not be out of place in a modern machine shop. From the silence of a 2,000-year-old shipwreck, a corroded lump of bronze and wood was hauled from the seafloor near the Greek island of Antikythera. To the salvage crew in 1901, it was an unidentifiable curiosity, a piece of junk from an ancient Roman cargo vessel. They had no idea they were holding the single most technologically complex object to survive from the ancient world. Decades of patient cleaning and study would slowly reveal its true nature, a stunningly intricate clockwork machine consisting of at least 30 interlocking bronze gears, precisely housed within a wooden case. This was the Antikythera Mechanism, a device so advanced it would not be recreated in complexity for over a millennium. It was not a weapon or a tool of war, but a sophisticated astronomical computer. By turning a hand crank on its side, an operator could set the gears in motion, calculating the positions of the Sun, the Moon, and the 5 known planets. It predicted lunar and solar eclipses with astonishing accuracy and even modeled the irregular orbit of the Moon, a subtle motion we now know is caused by its elliptical path. This required a level of mechanical engineering and astronomical understanding that historians believed was impossible for its time. The most shocking revelation came from advanced X-ray and surface imaging conducted in the early 21st century. Deep inside the calcified fragments, researchers discovered a complex system known as a differential gear. This is not a simple cogwheel. It is an assembly that calculates the difference between 2 rotational speeds. In the modern world, differential gears are what allow the wheels of a car to turn at different speeds when going around a corner. We thought this technology was invented in the 16th century for precision clocks and later adapted for automobiles. Yet here it was, functioning perfectly inside a Greek device from the 2nd century before Christ. The machine even came with its own ancient user manual, thousands of explanatory text characters etched onto its bronze plates, guiding the user through celestial calculations years into the future. So what does this mean for our story of progress? The Antikythera Mechanism stands as a stark, physical rebuke to the idea of a simple, linear technological ascent. It proves that a branch of ancient Greek science leaped forward to a conceptual peak that would then be completely lost for 1,500 years. Its existence forces us to ask a profound question. If this one device survived by pure chance in a shipwreck, how many other marvels of engineering were simply melted down for their metal, their secrets vanishing forever? The same Greek civilization that produced the Antikythera Mechanism nurtured a mind whose inventions bordered on magic. In the bustling intellectual hub of 1st century Alexandria, an engineer named Heron created a device that harnessed the raw power of steam. His design, known as the Eolipile, was deceptively simple. A hollow metal sphere was mounted on a boiler, with 2 nozzles bent to face in opposite directions. When the water boiled, steam rushed out through these angled pipes, causing the entire sphere to whirl with astonishing speed. Here was the fundamental principle of rotational force generated by steam, the very bedrock of our modern industrial world. Yet to Heron's contemporaries, this was not a source of practical power. It was a temple wonder, a philosophical demonstration, a fascinating toy that spun mysteriously without any apparent push or pull. They saw a clever novelty, completely missing the engine of an industrial age spinning right before their eyes. The same reactive thrust principle that spun Heron's sphere now propels jet aircraft across continents and spins the massive turbines that generate electricity for entire cities. Heron's genius, however, did not stop with steam. His surviving manuscripts reveal a mind obsessed with automation, a mind that had already mapped concepts we consider distinctly modern. He designed temple doors that would swing open automatically when a priest lit a ceremonial fire, using heated air to displace water and trigger a system of weights and pulleys. He sketched out a coin-operated machine that would dispense a measured amount of holy water. He even described a programmable cart that could be set to travel a predetermined path, powered by a falling weight and guided by a complex arrangement of ropes and pins. This was not merely a collection of gadgets. It was a coherent vision of an automated world, a world where machines responded to their environment and performed tasks without constant human guidance. So why did this vision fade into obscurity for nearly 2,000 years? The answer lies not in a lack of intelligence, but in a mismatch of context. Heron's society had abundant slave labor, diminishing the economic incentive to replace human muscle with steam power. The materials and precision manufacturing needed to scale his devices into robust, reliable machines simply did not exist. His inventions were brilliant solutions searching for a problem that his world did not yet feel urgently enough to solve. His blueprints were not failures. They were seeds planted in soil that was not yet ready to receive them. They proved that the ancient world stood on the very threshold of a technological transformation, holding the key but lacking the specific social and economic pressures to turn it. While Heron was engineering wonders in Alexandria, on the other side of the world, a Chinese scholar official was solving one of humanity's oldest and most terrifying problems. In the 2nd century, during the Han Dynasty, Zhang presented the court with a magnificent bronze vessel, a work of art that was also a revolutionary scientific instrument. This was the world's first seismoscope, a device designed to detect earthquakes from hundreds of miles away. Its design was as beautiful as it was brilliant. 8 dragon heads circled the ornate urn, each holding a heavy bronze ball in its jaws. Below them, 8 corresponding bronze frogs sat with their mouths wide open, waiting. The central mystery was how it worked, for Heng left no detailed internal blueprint. Historians and engineers now believe the secret was a cleverly suspended inverted pendulum hidden inside the vessel. When the faintest tremors of a distant quake traveled through the ground, the pendulum would swing, tripping a mechanism that caused just one dragon to release its ball. The clang of bronze hitting bronze would alert the court, and the specific frog that caught the ball would point directly toward the epicenter of the disaster. Imagine the awe of officials witnessing this machine announce a quake they could not even feel, days before messengers arrived on foot with news of the devastation. This was not magic, it was masterful engineering. Modern scientists have built and tested full-scale replicas of Zhang's design, using shaking tables to simulate earthquakes. The results are startling. The ancient seismoscope not only detects tremors reliably, but its directional accuracy is often perfect. It operates on the principle of inertia, the same fundamental law of physics that keeps you pressed back in your seat when a car accelerates quickly. The suspended pendulum inside the vase tends to remain still while the outer case moves with the ground, a concept we now call inertial seismology. Every modern seismograph on the planet uses this same core principle to measure the Earth's vibrations. Heng had mapped it out nearly 2,000 years ago, creating a functional tool that turned invisible seismic waves into an undeniable, clanging signal. His blueprint forces us to reconsider a common assumption that our understanding of physics has followed a simple, cumulative path. It reveals instead that brilliant, isolated insights into the laws of nature emerged in different cultures, achieving a practical sophistication that would not be matched again for centuries. Centuries after Heng's seismic detector, in the vibrant courts of 12th century Anatolia, an engineer named Ismail Al-Jazari was building machines that seemed to possess a life of their own. Serving the Artukid dynasty, Al-Jazari did not merely invent. He documented his work with breathtaking precision, compiling his life's work into the book of knowledge of ingenious mechanical devices. This was no simple catalogue, it was a comprehensive blueprint for a mechanical revolution, filled with designs for humanoid automata that could perform complex, lifelike tasks. One of his most famous creations was a waitress automaton, a graceful figure that would float on a lake during royal parties, serving drinks to guests. After a precise interval, she would automatically turn and return to her starting point to be refilled. This was not magic. It was achieved through an intricate system of water wheels, camshafts, and gears, a programmable sequence etched into brass and wood. His mechanical genius extended into the realm of music. Al-Jazari designed a programmable drum machine, a boat carrying 4 automated musicians that could be reconfigured to play different rhythms and patterns. By pegging small bumps onto a rotating wooden cylinder, an operator could create a musical sequence, a physical program that dictated when hammers would strike drums or cymbals. This is the direct mechanical ancestor of the modern music box and the digital drum machine, a machine storing and executing a performance program. Perhaps most striking to our modern sensibilities was his hand-washing automaton. When a servant poured water over a user's hands, a figure would emerge from a small door offering soap and a towel. Once the user was finished, the used water would automatically drain and a new basin of clean water would appear, complete with a flushing mechanism that feels eerily familiar. The entire cycle was automated through a sophisticated system of floats, siphons, and counterweights, a principle still used in modern plumbing. Al-Jazari's work represents something far greater than a collection of clever gadgets. He was systematically building the foundational concepts of robotics and sequential programming, all through mechanical means. His camshafts, which convert rotational motion into timed, linear movement, are still at the heart of every internal combustion engine today. His use of pegged drums to store and execute commands is the direct physical precursor to the punch cards that would program the earliest computers 800 years later. His blueprints demonstrate a continuous thread of innovation, proving that the dream of automation was alive and well in the medieval Islamic world, a dream so advanced it would not become a widespread reality until the 20th century. So why is his name not as famous as Leonardo da Vinci? The answer lies not in the quality of his work, but in the flow of history itself. His manuscripts, written in Arabic, remained largely within the sphere of the Islamic world, while the European Renaissance would later draw from different classical sources. His work stands as a powerful reminder that the spark of engineering genius can flare up brilliantly in any culture, at any time, only to be rediscovered when the world is finally ready to understand it. While Al-Jazari was perfecting his automata in the East, a different kind of renaissance was brewing in the workshops of Italy. Here, a single mind seemed to compress centuries of future engineering into a cascade of sketches. Leonardo da Vinci's notebooks are a universe of what-ifs, but one drawing stands out for its breathtaking leap of faith. Around 1480, he sketched a machine he called the aerial screw. It was a giant helix made of linen-covered wood, with a central shaft and a platform for a crew of 4. His notes explain that if this screw were spun fast enough, it would bite into the air, compressing it to achieve lift. He was describing, in essence, the fundamental principle of the helicopter rotor. There was no engine, of course. The power was to come from 4 men pushing on bars to rotate the entire apparatus. As a practical machine, it would never have left the ground. The materials were too heavy, the human power source far too weak, yet the concept was shockingly sound. He had correctly identified that a rotating, inclined plane could generate vertical thrust, a physical truth that would not be fully harnessed until the 20th century. This was not a random guess. Da Vinci's design was backed by his deep studies of air resistance and screw mechanics, a mathematical approach to a problem most considered pure fantasy. His helicopter was just one star in a constellation of futuristic ideas. In those same notebooks, you can find detailed blueprints for a pyramid-shaped parachute, which modern skydivers have proven to be entirely functional. He drew tanks with gears allowing for omnidirectional movement, and designs for massive crossbows and concentrated solar power using mirrors. Each of these concepts was a seed containing the complete genetic code for a technology that his world lacked the means to grow. Da Vinci's true legacy, then, is not in the machines he built, but in the future he so clearly saw. His work embodies a profound truth about human innovation. The blueprint must come first, a vision drawn in the mind long before the tools exist to make it real. His imagination laid the tracks that our engineering would eventually follow, proving that the first step toward building a new world is to dare to draw it. But could a civilization that mastered gears and steam also have harnessed the invisible power of electricity? In a museum in Baghdad sits a cluster of unassuming clay pots that have sparked one of the most heated debates in archaeological history. Known as the Baghdad Battery, these artifacts from the Parthian era, around the 1st century AD, are deceptively simple in construction. Each consists of a terracotta jar, inside which sits a rolled copper sheet, and within that, an iron rod. The jar would have been sealed with an asphalt or bitumen stopper, perfectly insulating the two metals from each other. The critical missing ingredient was a liquid. When the jar is filled with an acidic electrolyte, something as common as vinegar or grape juice, a chemical reaction occurs. The acid reacts with the iron and copper, causing electrons to flow from one metal to the other through the liquid, creating an electric current. Modern reconstructions have consistently shown that a single cell can generate between 1 and 2 volts of electricity. This is not a tremendous amount, but it is a measurable, usable current. The question that has divided experts for decades is, what was this current used for? One compelling theory is electroplating, the process of using electricity to deposit a thin layer of one metal, like gold, onto the surface of another, like silver. Artisans of the era were masters of gilding, and a mild electrical current would have provided a remarkably efficient method for bonding metals compared to purely chemical techniques. Another possibility involves the tingling sensation this current would produce on the skin. It could have been used for mild medical or ritualistic stimulation, a form of ancient physiotherapy or a mystical experience intended to demonstrate a priest's connection to unseen forces. The true purpose may never be known for certain, and many scholars remain skeptical of its use as a practical power source, yet the physical principle is undeniable. This clay pot is a functional electrochemical cell, a basic battery. Its existence suggests that the fundamental concept of generating and channeling electricity was not born in the 18th century with scientists like Galvani and Volta, but was potentially understood, at least in a rudimentary form, nearly 2,000 years earlier. Whether it was a tool for craftsmen, a device for healers, or a sacred object for temples, the Baghdad Battery forces us to confront a startling possibility. The spark of electrical innovation may not have been discovered in the Age of Enlightenment, but quietly flickered to life in the dim light of a Mesopotamian workshop, only to be extinguished and forgotten for centuries. The concept of a programmable machine was already a reality in the theaters of ancient Greece. While Heron was building his Automata in Alexandria, another engineer, Phylon of Byzantium, was constructing something even more ambitious, an entire theatrical performance run by machines. His automated theater was not a simple puppet show. It was a sophisticated robotic spectacle capable of staging a complete play without a single human performer on stage. Through an intricate clockwork of ropes, weights, and precisely carved rotating drums, mechanical actors would appear, move with purpose, and deliver their lines through pre-recorded sound mechanisms. The theater itself was a participant, changing entire scenes and producing sound effects like thunder at the exact right moment, all driven by a single central power source. The true genius of Phylon's design, however, lay in its programming. The sequences of actions were dictated by pins strategically placed on rotating wooden cylinders. As these cylinders turned, the pins would engage with levers and gears, triggering specific events at precise times. A pin here would make a figure emerge from behind a column. A pin there would cue the sound of a wave crashing, and another would lower a new backdrop into place. This system of raised pins and empty spaces is a form of binary language, a physical code of on and off commands that is the direct mechanical ancestor of the punch cards used in early 20th century computers and the fundamental binary logic that powers every digital device today. Phylon's theater was in essence a mechanical computer whose output was not calculation but drama. It proves that the core concept of programming, of storing a sequence of instructions for a machine to execute automatically, was not born in the Silicon Age. It was conceived in the classical world, realized in wood and bronze, and used to tell stories, demonstrating that the human drive to blend technology and art, to create machines that mimic life, is a blueprint as old as engineering itself. The Pantheon in Rome still holds the record for the world's largest unreinforced concrete dome, a crown it has worn for nearly 2,000 years. Its survival is a silent rebuke to our own crumbling infrastructure, where modern concrete bridges and parking garages often require major repairs after just 50 years. The secret to this staggering longevity was not magic, but a masterful material science that was lost for over a millennium. Roman concrete was a different substance entirely from the Portland cement we use today. Modern concrete is brittle and prone to cracking, which allows water and chemicals to seep in, corroding any steel reinforcement and causing the structure to fail from within. The Roman recipe was fundamentally different and far more resilient. They mixed lime and volcanic ash, specifically a type of ash from the Italian town of Pozzuoli, with chunks of rock and brick. The real genius, however, was in the final ingredient, seawater. For centuries, we assumed using salt water was a mistake, a primitive compromise. We were completely wrong. Recent analysis using advanced microscopes has revealed a stunning chemical process. When seawater percolates through the Roman concrete, it reacts with the volcanic ash and lime to form rare, plate-like crystals. As tiny cracks begin to form, water seeping into these fissures actually triggers the growth of these new crystals, which effectively fill the gaps. The concrete does not just resist damage, it actively heals itself. It is a living material, growing stronger over centuries, not weaker. The precise formula and mixing techniques were a closely guarded secret of the Roman military engineers, a secret that vanished in the administrative collapse of the empire. The knowledge of how to create this self-regenerating stone was simply forgotten, a casualty of fractured trade routes and lost institutional knowledge. Modern materials scientists are now racing to reverse engineer this ancient process, hoping to incorporate these self-healing properties into our own concrete. This means the blueprint for a more sustainable, durable future of construction was not invented in a lab, but was lying in plain sight all along, in the silent, enduring bulk of 2,000-year-old harbors and temples. This forgotten formula forces us to ask a humbling question: how many other solutions to our modern problems are already written in the stones of the past? From the quiet genius of self-healing concrete, we now turn to a weapon that roared across the water. The Byzantine Empire guarded a naval secret so potent it could decide the fate of empires, a substance known simply as Greek fire. In the 7th century, as enemy fleets closed in on Constantinople, Byzantine ships would unleash this horror. It was a liquid flame that did not just burn, it clung to everything it touched. Most terrifying of all, it could not be put out with water, often burning even more fiercely when doused, turning the sea itself into a sheet of fire. This was not merely a weapon of terror, it was a sophisticated chemical and mechanical system, a blueprint for a controlled inferno. The secret was not just in the mysterious fluid, but in its delivery. Mounted on the prows of their warships were bronze tubes connected to large pressurized containers and pumps. Operators would use a powerful hand pump to build pressure, then open a valve, projecting the sticky, ignited liquid in a continuous stream or a roaring plume over the water, much like a modern flamethrower. Historical accounts describe the siphons as being mounted on a swivel, allowing the jet of fire to be aimed at enemy ships and boarding parties with devastating precision. Some versions of the system even included a heating mechanism to pre-warm the substance, ensuring it would ignite instantly and flow easily under pressure. The engineering behind this was remarkably advanced, a carefully balanced system of fluid dynamics, pressure control, and metallurgy. The exact formula for the fire itself was the most closely guarded state secret of the age. Emperors passed the knowledge only to their heirs, and the chemists and engineers who worked on it were sworn to absolute secrecy. Modern chemists have proposed many theories for its composition, suggesting it might have been a cocktail of crude petroleum, quicklime, sulfur, or even nitrates. The key to its water-resistant property likely lay in the inclusion of a form of calcium phosphide, which releases flammable phosphine gas upon contact with water, or quicklime, which generates intense heat when mixed with water, reigniting any floating fuel. Yet no modern reconstruction has ever perfectly matched the terrifying descriptions from historical chronicles. The secret died with the Byzantine Empire. As the empire crumbled and its administrative structures collapsed, the precise knowledge of how to mix the chemicals and operate the complex pumps was lost forever. This was not a gradual forgetting, it was a complete and total erasure of a technology. The loss of Greek fire is a stark lesson in how advanced engineering can be held hostage by politics and conflict, vanishing overnight when the civilization that nurtured it falls. The blueprint for this ancient weapon of mass destruction is a ghost, a reminder that some of history's most powerful innovations were so effective, they were secrets their creators took to the grave. A weapon of pure light forged the greatest scientific legend of the ancient world. During the Roman siege of Syracuse in the 3rd century BC, the brilliant mathematician Archimedes is said to have deployed a terrifying new defense. According to accounts written centuries later by authors like Lucian and Anthemius, he arranged a series of highly polished bronze shields to act as mirrors, focusing the intense Mediterranean sunlight onto the wooden hulls of the invading Roman fleet. The concentrated beam generated such intense heat that the ships reportedly burst into flames long before they could reach the shore. For generations, historians dismissed the story as a myth, a fanciful tale meant to glorify a genius. The idea of a death ray seemed too much like science fiction to be credible, yet this forgotten blueprint for concentrated solar power has refused to fade into obscurity. In the modern era, the legend has been put to the test. In 1973, a Greek scientist, Ioannis Sakkas, conducted a large-scale experiment using 70 mirrored copper shields, each coated with a reflective surface, to focus sunlight on a wooden replica of a Roman galley moored nearly 200 feet away. The result was unequivocal. Within seconds, the targeted area of the ship's hull charred and then burst into flame. A team from the Massachusetts Institute of Technology later attempted a similar test in 2005. And while they found the challenge of holding a steady focus on a moving ship significant, they confirmed that the basic principle was absolutely sound. The necessary technology, polished bronze, was readily available to Archimedes. The underlying science of parabolic reflectors was within his profound understanding of geometry. So whether the event happened exactly as described is almost beside the point. The mere existence of the story reveals a revolutionary mindset. Over 2,000 years before the first modern solar power plants were built, a mind in the classical world was already conceptualizing how to weaponize a renewable energy source. Archimedes was not just thinking about levers and pulleys, he was mapping the fundamental relationship between light, heat, and geometry. This blueprint, preserved in legend, demonstrates that the potential of solar energy was not a 20th century discovery, but an ancient intuition waiting for the right technology to bring it to life on a global scale. Long before magnetic needles swung in compasses, a different kind of directional device rolled through ancient China, its secret hidden not in magnetism but in mathematics. The south-pointing chariot was an engineering marvel of the 3rd century, a lavish ceremonial vehicle topped with a small, outstretched figure that perpetually pointed toward the south. No matter how sharply the chariot turned or how many circles it traveled, the figure on top, often a carved immortal or a celestial official, would slowly rotate on its platform to correct its position, its finger never wavering from its true bearing. This was not magic, but a masterpiece of mechanical computation. Inside the ornate carriage lay a breathtakingly complex arrangement of gears, including a differential gear system strikingly similar to the one found in the Antikythera Mechanism. As the chariot's wheels turned, they drove this hidden gear train. The genius of the design was in its compensation. The gears were arranged to calculate the difference in rotation between the two wheels. When the chariot moved in a straight line, both wheels turned at the same rate and the figure remained static. But when it turned a corner, the inner wheel necessarily rotated slower than the outer one. The differential gears detected this difference and translated it into a precise, counteracting rotation for the figure on top, keeping it locked on its southern orientation. This was a mechanical feedback system, a physical algorithm etched into bronze and wood that could solve a complex navigational problem in real time. The most remarkable part of its story is not its initial invention, but its repeated disappearance and revival. The knowledge of how to build the south-pointing chariot was lost and then independently rediscovered at least 4 times over 1,000 years of Chinese history. Each time, a different engineer, from the legendary Ma Jun in the 3rd century to the court engineer Wu Deran during the Song dynasty, would recreate the device, often refining the gear ratios and improving its accuracy. This cycle of loss and recovery reveals a profound truth about technological knowledge. It can be so fragile, so dependent on a single thread of understanding, that it can vanish from an entire culture, only to be painfully reborn from first principles by a later genius. The chariot itself had little practical use on the battlefield or for travel. Its value was symbolic, a dazzling display of imperial ingenuity. Yet its underlying blueprint was a direct mechanical predecessor to the inertial guidance systems that navigate modern aircraft and spacecraft. It proves that the core concept of dead reckoning, of calculating your position based on your own movements, was being solved not with electronics, but with intricate clockwork, a full millennium before the West would develop similar mechanisms. How many other elegant mechanical solutions have been forgotten, their principles waiting to be unearthed not from the ground, but from the pages of a neglected manuscript? While the south-pointing chariot calculated direction through gears, another Alexandrian engineer was mastering the flow of time itself. In the 3rd century BC, Ctesibius confronted a fundamental flaw in ancient timekeeping. Simple water clocks, which just dripped from one jar to another, would slow down as the water level dropped, losing precious minutes every hour. His brilliant solution was not to fight the flow of water, but to regulate it with absolute precision. He designed a massive, multi-tiered system where water first poured into a primary reservoir that was kept perpetually full by an overflow channel. This ensured the water pressure feeding the main timekeeping mechanism remained perfectly constant, creating a steady, unvarying trickle into the measuring vessel below. The result was a clock that could keep time with an accuracy that would not be surpassed for over 1,000 years. But Ctesibius did not stop there. His clock was a true marvel of integrated engineering. A floating figure would rise steadily in the measuring vessel, its rod pointing to the hour on a vertical scale. And because the length of an hour changed with the seasons in the ancient world, he incorporated interchangeable cylinders with different hour markings for different times of the year. Imagine a device you had to physically recalibrate for summer and winter, a mechanical acknowledgement of the Earth's tilt. The clock was also programmable. It featured an elaborate alarm system where pebbles would be dropped onto a gong or trumpets would sound at a preset time, triggered by the rising float. Some accounts even describe miniature automated theaters with moving figures that would perform on the hour, all powered by the same relentless, regulated flow of water. This was not just a timekeeper, it was an ancient smart clock, a central hub of automation. The core principles Ctesibius established, the use of feedback from the overflow to maintain a constant state, and the translation of a fluid's motion into complex mechanical actions, are the bedrock of modern hydraulic engineering and process control systems. Every chemical plant, every automated factory that uses fluid levels to regulate its operations is echoing a 2,000-year-old design from an Alexandrian workshop. His blueprint proves that the pursuit of precise, automated control over our environment is not a modern obsession, but a very ancient one, solved with an elegance we are only now coming to fully appreciate. The relentless pursuit of control over water seen in Ctesibius's clock finds its ultimate expression not in a single machine, but in the bones of an entire city. 5,000 years ago, in what is now Pakistan, the Indus Valley civilization built metropolises like Mohenjo-Daro, whose very streets were a blueprint for a healthy urban life. Walking through its ruins, you are not looking at a haphazard collection of ancient huts, but at a meticulously planned grid of wide, straight streets that intersected at perfect right angles. This was not an organic growth, it was a master plan drawn in clay and brick long before the concept of urban planning even existed elsewhere. Every house, from the smallest dwelling to the largest structure, was connected to a city-wide drainage system of astonishing complexity. Earthenware pipes carried wastewater from individual homes into brick-lined channels that ran beneath the main streets, all covered with sturdy slabs for easy maintenance and to contain odors. These channels sloped gently but precisely, ensuring a constant flow toward the outskirts of the city, a gravity-fed sewage system that would not become standard in European cities for another 4,000 years. The entire city was elevated on massive mud brick platforms, protecting it from seasonal floods, a testament to an engineering foresight that understood its environment completely. This was a civilization that had standardized the very brick itself, using perfectly uniform, kiln-fired bricks in a consistent ratio of 4:2:1, creating a modular building block that allowed for rapid, orderly construction and incredible structural stability. The crown jewel of this hydraulic mastery was the Great Bath. This massive, watertight pool, lined with precisely fitted bricks and a thick layer of natural bitumen, was essentially an ancient municipal swimming pool or a center for ritual purification. The bitumen, a tar-like substance, acted as a perfect sealant, preventing water from seeping into the ground for centuries. Surrounding the bath were small changing rooms and an elaborate system for filling and emptying the tank with fresh water from a dedicated well. The entire complex speaks of a society that prioritized public health, community, and a sophisticated understanding of civil engineering on a grand scale. Then, around 1900 BC, this entire civilization, with all its knowledge, went into a profound decline. The reasons are still debated, but the result was catastrophic. The cities were abandoned, and the blueprints for this harmonious urban existence were forgotten. The knowledge of standardized construction, city-wide sanitation, and flood-resistant architecture simply evaporated from human history. When the Romans later built their aqueducts and sewers, they were not improving upon an Indus Valley design. They were independently rediscovering principles that had been perfected and then lost millennia before. The silent, orderly streets of Mohenjo-Daro stand as a haunting question. How different might our own urban history have been if this 5,000-year-old blueprint for a clean, well-ordered city had never been misplaced? Norse sagas speak of a sunstone, a magical crystal that revealed the sun's position on the gloomiest, most overcast days. For generations, historians dismissed this as pure myth, a poetic metaphor for Viking navigational skill. But science has since uncovered a stunning truth buried within these legends. The Viking sunstone was likely a piece of Iceland spar, a transparent calcite crystal that possesses a remarkable property. It polarizes light, filtering its waves into a single, clear direction. On a cloudy day when the sun is completely hidden, the sky still emits a subtle pattern of polarized light, with the polarization forming a ring centered on the sun's location. A navigator would hold the crystal up to the sky and rotate it. When the light passing through the crystal appeared at its brightest, the crystal's alignment would point directly toward the hidden sun, even through thick fog or the dim twilight of the northern latitudes. This was not magic, it was a practical application of optical physics, a technology born from centuries of empirical observation. With this simple stone, Viking sailors could confidently plot their course across the vast, featureless North Atlantic, reaching Iceland, Greenland, and even the coast of North America centuries before other European explorers. Their secret weapon gave them a staggering navigational advantage long before the magnetic compass became widely known in Europe. The underlying science of how and why this worked, the formal study of light polarization, would not be established until the 19th century. This forgotten blueprint reveals a profound pattern in human innovation. A technology can be perfectly functional, even revolutionary, long before the civilization using it possesses the formal scientific vocabulary to explain why it works. The Vikings did not need to understand wave theory. They simply needed to observe that the crystal showed them the way. Their sunstone stands as a powerful testament to the fact that discovery often begins not in a laboratory, but in the hands of a practical mind, solving a real-world problem with the tools the world provides. While the Vikings navigated by polarized light, another civilization was mastering the very air they breathed. In the scorching deserts of ancient Persia, architects developed a revolutionary system that turned brutal heat into cool comfort without a single moving part. These were the Windcatchers, elegant towers that rose from the rooftops like silent sentinels, harnessing the desert winds to create nature's own air conditioning. Their design was a masterpiece of intuitive thermodynamics. A windcatcher is essentially a tall, chimney-like structure with openings facing the prevailing wind. As the hot, dry breeze is captured at the top, it is funneled down into the heart of the building. But the real magic happened below ground. This incoming air was often directed through underground channels called qanats, where it would pass over cool, fresh water from deep aquifers or across moist clay surfaces. The air would shed its heat, cooling dramatically through evaporation before flowing upward into the living spaces, creating a continuous, refreshing draft. Some of these passive systems could drop the indoor temperature by a staggering 15 degrees Celsius compared to the blistering heat outside. This was not just a clever trick, it was a sophisticated application of principles we now call fluid dynamics and evaporative cooling, concepts that would not be formally defined by scientists for over 1,000 years. The entire structure was a single, integrated machine carved from earth and brick, responding silently to the environment. Modern architects and engineers, now grappling with the enormous energy demands of mechanical cooling, are looking back at these ancient blueprints with newfound respect. The principles of the Persian Windcatcher are being revived in contemporary sustainable design, inspiring buildings that use natural ventilation stacks, geothermal cooling, and thermal mass to regulate temperature with minimal electricity. This ancient innovation forces us to reconsider our relationship with energy. It suggests that the most elegant solutions to our modern challenges may not always lie in greater complexity, but in a deeper, more intelligent collaboration with the natural world. How many other energy-saving secrets are waiting to be unearthed from the architectural wisdom of the past? High in the Andes, woven grass cables danced across terrifying gorges, defying the very logic of the mountains. These were the Inca suspension bridges, masterpieces of pre-Columbian engineering that turned flexible grass into pathways capable of supporting an army. The Spanish conquistadors who arrived in the 16th century recorded their stunned disbelief. Men on horseback and even heavy artillery, could cross these swaying spans that stretched over 150 feet above raging rivers. They looked impossibly fragile, yet they held season after season for over 500 years. The secret was not in a single, permanent structure, but in a living tradition of renewal. Each bridge was a communal project, with every household in a village contributing a length of rope woven from a local, resilient grass. The strongest fibers were twisted into cables thicker than a man's torso, an organic steel that carried the entire weight of the bridge and its travelers. The engineering principle was pure genius, a perfect mirror of the cable-stayed bridges we build with steel and concrete today. The massive main cables, anchored deep into stone towers on either side of the canyon, handled the immense tension, the pulling force. The deck of the bridge, a woven mat of smaller fibers, hung from these primary cables, managing compression and distributing the load evenly across the entire structure. This elegant balance of tension and compression is the same fundamental physics that allows modern engineers to span vast distances. The most profound aspect of this blueprint, however, was its relationship with time. The Incas did not build a bridge to last forever. They built a bridge to be reborn. In a powerful annual ceremony, the old bridge was cut loose to tumble into the river below, and the entire community would gather to weave its replacement, braiding the new cables by hand and pulling them taut across the chasm. This was not a sign of primitive technology, but a sophisticated understanding of sustainable engineering. They accepted the natural life cycle of their organic materials and turned maintenance into a sacred, social ritual, ensuring the knowledge of construction was passed down through every generation. This forgotten blueprint challenges our modern obsession with permanence. It proves that sophistication is not always measured in millennia of endurance, but sometimes in the wisdom of a system that renews itself, a bridge that was always simultaneously both ancient and new. A blade forged in medieval fires could slice clean through a rival sword, then bend nearly double before springing back to perfect straightness. This was not fantasy, but the documented reality of Damascus steel, a metallurgical secret lost to time. The legendary swords, named for the Syrian city that traded them, were famed from the Crusades to the Mughal Empire for their otherworldly combination of lethal sharpness and incredible flexibility. Their surfaces shimmered with a characteristic watery pattern, a visual signature of a material structure unlike any other. For centuries, the method of their creation remained a complete mystery, vanishing in the 1700s as the last master smiths took their knowledge to the grave. Modern science has only recently begun to unravel the secret, and the findings are staggering. When samples of authentic Damascus steel are placed under electron microscopes, they reveal structures that should not exist in medieval metal. Researchers have identified carbon nanotubes and incredibly hard cementite nanowires woven directly into the steel matrix. These are not simple impurities. They are sophisticated nanostructures that act as a natural composite, simultaneously preventing the propagation of cracks while allowing the blade to flex and providing microscopic serrations that enhance its cutting edge. This means medieval blacksmiths, working entirely by eye and tradition, were unknowingly engineering materials at the nanoscale. Their precise process began with a specific type of high-purity iron ore sourced from India, known as wootz steel. This raw material was melted in a sealed clay crucible with carbon-rich organic matter like leaves or wood, then cooled very slowly over many days. The resulting ingot, already patterned from this controlled crystallization, was then heated to a very specific, non-melting temperature, a precise orange heat that master smiths could judge by the color of the sun at dawn. They would hammer and fold the metal at this exact thermal window, a delicate dance that aligned the internal crystalline structure without destroying the precious carbon nanotubes. The final quenching, the plunge into a cooling liquid, locked this nano-reinforced architecture into place. The loss of this formula was a catastrophe for materials science. It was not a single event, but a slow fading. The specific mines were exhausted, the exact temperature control cycles were never written down, and the apprentice-based system of knowledge transfer eventually broke. Today, modern metallurgists using electric furnaces and scanning electron microscopes can create steel that visually mimics the watery pattern, but they have yet to fully reproduce the perfect blend of nanostructures that gave the original its legendary performance. This forgotten blueprint forces us to see ancient craftsmanship in a new light. These smiths were not just artisans, they were experimental material scientists who perfected a recipe through generations of trial and observation, achieving results that our own science is still struggling to explain and duplicate. Their lost art stands as a humbling reminder that some of history's most advanced engineering was performed not in a laboratory but at the forge. The steady click of a stone dropping into a metal box marked the passing of each Roman mile. Within the bustling workshops of Alexandria, engineers like Heron and the Roman architect Vitruvius perfected a device of elegant simplicity, the Odometer. This was no simple wheel rotation counter, but a miniature mechanical computer housed on a cart, translating the raw data of distance into precise, tangible measurements. As the cart's wheel turned on a long journey, it rotated a single vertical pinion gear. The true genius lay in the gear train that followed. This series of interlocking gears was meticulously calculated with a 400-to-1 ratio, meaning that for every 400 rotations of the cartwheel, the final gear in the sequence would complete exactly one full turn. Attached to this final gear was a cleverly positioned peg. With each full rotation, the peg would catch a small stone held in a reservoir and tip it, dropping it with an audible clatter into a waiting container below. Every clink represented another mile accurately logged, a physical tally of the road traveled. This system automated the tedious work of surveyors and merchants, transforming an endless journey into a countable, reliable metric. The underlying principle was a form of mechanical digitization, a physical bit of information represented by a falling stone. The gear ratios performed a mathematical operation, division and conversion, long before the invention of the electronic calculator. This blueprint reveals a world already thinking in terms of automated data collection, where a machine could reliably observe, calculate, and record information far more accurately than a human ever could. The next time your car's digital dashboard ticks off another tenth of a mile, remember the ghost of that ancient cart, its gears quietly counting the stones that measured an empire. Long before the first film projector flickered to life, a Han Dynasty inventor was already mastering the illusion of motion. In 2nd century China, a device known today as the zoetrope was not a Victorian novelty, but an ancient experiment in visual storytelling. It was a simple yet brilliant construction, a hollow drum mounted on a vertical axis so it could be spun freely. The inside of this drum was lined with a paper band depicting a sequence of images, each one a subtle progression from the last, showing a galloping horse or a kneeling archer drawing his bow. The outer wall of the drum was pierced with a series of narrow vertical slits. A viewer would spin the drum and peer through these slits as they whipped past. Instead of a blur, they would witness a magical transformation, the individual images merging into a single, fluid, moving picture. The gallop became a continuous run. The archer smoothly released his arrow. This was the birth of animation, powered by a profound understanding of a quirk of human biology called persistence of vision. Our brains retain an image for a fraction of a second after it is gone. The slits in the drum acted as a shutter, allowing the viewer to see only a brief, clear flash of each image. The brain, striving for continuity, seamlessly stitches these flashes together, creating the illusion of movement from a series of still frames. This is not merely an interesting historical footnote, it is the absolute bedrock of all cinematic technology. Every animated film, every motion picture, from the earliest black and white reels to the most advanced digital effects, operates on this exact same principle. The ancient Chinese zoetrope was, in its essence, a mechanical film projector, lacking only a light source. Its existence shatters the conventional timeline of media technology. We often think of animation as a child of the industrial age, but this blueprint reveals a different story. A story where the fundamental concept of capturing and replaying motion was conceived in an era of silk and bamboo, a full 17 centuries before it would be rediscovered and industrialized in the West. Why did this idea not lead to an ancient cinematic revolution? Perhaps like Heron's steam engine, it was a solution too far ahead of its societal context, seen as a delightful philosophical toy rather than the seed of a new art form. It stands as a quiet testament to an enduring human desire, not just to capture a moment in time, but to breathe life into it, to make the still image dance. A Roman aristocrat could stroll barefoot across his marble floors in the dead of winter, feeling only a gentle, pervasive warmth rising from the stone itself. This comfort was not magic, but the product of an engineering marvel known as the hypocaust system, a form of central heating so effective its principles would not be widely replicated for over 1,500 years. The system began with a furnace, a perpetual fire stoked by slaves or servants in a basement-level chamber. But instead of letting the hot air and smoke escape directly upwards, Roman engineers channeled it with brilliant precision. They raised the floor of the room above on a grid of short, sturdy brick pillars, creating a hidden, hollow space beneath the entire surface. The hot gases from the furnace would flow into this subterranean plenum, slowly and evenly heating the massive stone or concrete floor slabs above. In the most advanced designs, the heat did not stop there. Terracotta pipe boxes were embedded within the walls themselves, creating flues that captured the rising heat and warmed the plaster and brick before the smoke finally escaped through vents in the roof. This transformed entire walls into radiant surfaces, heating the room from all directions. The system was a masterclass in thermodynamics, leveraging convection, radiant heat, and thermal mass. The thick floors and walls, once heated, would retain that warmth for hours, ensuring a stable, comfortable environment long after the furnace fire had died down to embers. This technology powered the vast public bathhouses that were the social hearts of Roman cities, from the damp chill of Britain to the cool nights of North Africa. It was a cornerstone of Roman public health and domestic luxury, yet with the collapse of the empire and the fragmentation of its technical knowledge, the hypocaust became a forgotten art. The fuel-intensive system was too complex and costly for the fractured societies that followed. The dark, cold halls of medieval castles were a direct consequence of this lost blueprint. It was not until the 19th century, with the advent of steam and hot water systems, that Western civilization reinvented a method of whole building heating that could rival the comfort enjoyed by the Romans. This forgotten system asks us a simple but profound question about our own modern comforts. How many of them are truly new inventions, and how many are merely rediscoveries of ancient genius, reborn with new materials and power sources? A dark room could become a window onto the sun itself. In 10th century Cairo, the brilliant scientist Ibn Al-Haytham, known in the West as Al-Haytham, transformed a simple optical curiosity into a precise instrument of discovery. Earlier thinkers had noted that light passing through a tiny hole into a darkened space would project an inverted image of the outside world onto the opposite wall. But they saw it as a mere novelty. Al-Haytham saw a laboratory. He meticulously described this device, the camera obscura, in his revolutionary book of optics, using it to prove a fundamental law that light travels in perfectly straight lines. He demonstrated how every point of a luminous object, like a candle, emits rays in all directions, but only the single ray from each point that could travel straight through the aperture would succeed, painting a perfect, though upside-down, replica of the scene outside. This was more than observation. It was a rigorous experimental method that laid the entire foundation for the science of optics. His work detailed the properties of lenses for magnification and studied the nature of reflection and refraction, the bending of light as it passes through different materials like water or glass. He systematically dismantled earlier Greek theories of vision that claimed rays emanated from our eyes, proving instead that we see because light from objects enters them. His detailed descriptions of curved lenses and precise image projection techniques were essentially blueprints for technologies that would not be realized for another 600 years. Every modern camera, from the one in your smartphone to the largest telescope, operates on the very principles Al-Haytham established in that darkened room. His forgotten work forces us to confront a pivotal moment where scientific methodology itself was being forged, where observation and experiment began to triumph over pure philosophical reasoning. It shows that the path to our visual world of photography and film was not illuminated by the flash of a Renaissance genius, but was patiently mapped out by a medieval mind in a silent chamber, watching an inverted world dance upon the wall. Standing in a Delhi courtyard for 16 centuries, a 23-foot iron pillar defies every expectation of metal. While modern steel structures require constant painting and maintenance to fight off rust, this ancient monument has withstood monsoons, scorching heat, and pollution with barely a blemish. It is not made of some alien alloy, but of wrought iron, the same material used in countless relics that have long since returned to the earth as reddish dust. The secret to its immortality was not a magical coating, but a brilliant mistake in its original recipe, a flaw that became its greatest strength. Modern metallurgists who have analyzed the pillar discovered its iron contains an unusually high amount of phosphorus, a result of the specific iron ore and the unique forging process used by the ancient Indian blacksmiths. These smiths did not use a blast furnace as we do today. Instead, they hammered and folded the iron while it was solid, a technique that mixed in charcoal and other impurities from the fuel in a very specific way. This created a thin, protective passive film on the surface, a glassy layer of iron hydrogen phosphate that acts as an invisible, self-renewing shield against moisture and oxygen. It is a perfect, natural form of corrosion protection, engineered entirely by accident over 1,600 years ago. The tragedy is that the precise, multi-step manufacturing blueprint for this wonder was lost. We know the what, but we have forgotten the how. Contemporary engineers attempting to recreate the pillar's rust resistance using period-accurate methods have consistently failed. Our modern industrial process removes phosphorus as an impurity because it makes steel brittle for construction and machinery. We optimized for strength and malleability, inadvertently sacrificing the secret to eternal metal in the process. This forgotten blueprint forces a humbling realization. Ancient craftsmen, working without chemical theory, achieved a material property through empirical, hands-on techniques that our advanced science is still struggling to reverse engineer. Their knowledge was not written in a manual, but embodied in the rhythmic strikes of their hammers and the color of the fire, a tactile wisdom that vanished when its last practitioners did. A civilization that flourished deep in the Central American rainforest mapped the heavens with a precision that would not be matched for centuries. Within the pages of the Dresden Codex, one of the few surviving Mayan books, lies a set of astronomical tables so advanced they could predict cosmic events decades into the future. These were not vague prophecies but precise calculations, forecasting the appearances of Venus as the morning and evening star, predicting solar eclipses, and tracking the complex cycles of the moon. The Mayan astronomers achieved this not with telescopes but with generations of naked eye observation and a mathematical system of breathtaking elegance. They counted in base 20, a decimal system likely rooted in the number of human fingers and toes, and they had a concept for zero long before it appeared in European mathematics. This allowed them to perform immense calculations and work with very large numbers, charting celestial patterns over vast stretches of time. But their true genius lay in their recognition that the cosmos is not perfectly regular. They knew, for instance, that the solar year is not exactly 365 days long. Their calculations incorporated sophisticated correction factors, adjusting their long-term calendars to account for the slight discrepancies that would otherwise throw their predictions out of alignment over centuries. They were essentially applying a form of ancient calculus to smooth out the imperfections of orbital mechanics. The tables in the Dresden Codex are a working document, a celestial almanac used by priest astronomers to maintain the cosmic order they believed was essential for their world. The accuracy of their Venus tables, for example, is stunning, pinpointing the planet's 584-day cycle with an error of just 1 day in 500 years. This level of predictive power was on par with, and in some cases surpassed, the astronomical work being done in Europe during the same period. Yet this entire intellectual edifice was shattered in the 16th century. The Spanish conquest was not just a military defeat, it was a cultural and intellectual cataclysm. Catholic priests, viewing the Mayan codices as pagan works, systematically gathered and burned them in massive auto-da-fés. The Dresden Codex is a rare survivor, one of only 4 known complete Mayan books. With the destruction of the libraries, the specific methods of calculation, the nuanced correction factors, and the deep observational traditions were erased. The priest astronomers who held this knowledge perished, and the living chain of transmission was broken forever. This was not a gradual fading, but a sudden, violent deletion of an entire scientific paradigm. The blueprint preserved in the Dresden Codex is a ghostly remnant, a testament to a sophisticated knowledge system that looked to the stars and saw not mystery but mathematics, a system that understood the heavens well enough to predict their dance, only to have that understanding extinguished in the fires of conquest. Fire transformed from a sacred symbol into a mechanical servant within the temples of Alexandria. Heron's design for automatic temple doors was a masterclass in energy conversion, a hidden performance where heat, water, and metal worked in perfect concert. Picture the scene: a priest lights the ceremonial altar fire, not knowing he has just become the operator of a complex machine. The flames would heat a sealed container of water hidden beneath the altar, a simple bronze kettle acting as the system's heart. As the water boiled, steam pressure would build, forcing air through a pipe and into a second, hidden vessel. This secondary container held a counterweight, and as the pressurized air displaced water within it, the counterweight would slowly rise. The rising weight, in turn, pulled on a rope or chain wound around a spindle, causing the massive temple doors to swing open as if by an invisible hand. The entire process was silent, seamless, and to a worshipper, utterly miraculous. The doors seemed to open in direct response to their devotion, a divine acknowledgement of their offering. This was not merely a clever trick, it was a practical application of thermodynamics, converting thermal energy from the fire into the mechanical work of opening heavy doors. Heron had built a single piston steam engine, using steam not to turn a wheel but to perform a specific, repeatable task. The principles at play, the expansion of gases, the transfer of pressure through a fluid, and the use of counterweights for controlled motion, are the absolute bedrock of mechanical automation. Yet this incredible invention remained a temple wonder, a spectacle confined to a religious context. The economic and social conditions that would have demanded the widespread application of such automation simply did not exist. There was no pressing need to replace human labor when that labor was abundant and inexpensive. The materials needed to scale this technology, to contain higher pressures and perform heavier work, were not yet available. So this brilliant blueprint for an automated age remained just that, a blueprint, a stunning preview of a technological path not taken. It proves that the conceptual leap from fire to mechanical work was made not in 18th century Britain, but in 1st century Egypt, a leap that would then be forgotten, forcing humanity to wait nearly 2,000 years to learn the same lesson all over again. The true marvel of Zhang Heng's seismoscope lies not in its bronze dragons, but in the silent, unseen mechanism within. While we know the vessel detected quakes from hundreds of miles away, the precise engineering that translated a faint tremor into a single, precise release remains one of history's great mechanical puzzles. Historical accounts describe an inverted pendulum suspended inside the ornate urn, a cleverly balanced weight that would tend to stay still as the earth moved around it. The challenge was one of sensitivity versus stability. The pendulum had to be exquisitely responsive to the faintest vibrations, yet not so delicate that it would trigger from a passing cart or a slamming door. Ancient texts hint at a system of levers and release mechanisms, likely involving a carefully balanced pin or a hook that would dislodge only when the pendulum swung with a specific, calibrated force. This was not a simple on-off switch. It was a mechanical brain designed to distinguish a seismic wave from everyday noise. Modern engineers attempting to recreate the device have faced this exact problem. Their reconstructions, based on the same historical clues, often produce a device that works, but not with the legendary accuracy described in the ancient chronicles. Some models are too sensitive, dropping multiple balls for a single event, while others are not sensitive enough, failing to react to smaller tremors. This disparity suggests that Zhang Heng and his artisans possessed a nuanced, tactile understanding of vibration physics and friction that is not fully captured in the written descriptions. They knew exactly how much to polish a pivot point, how to balance a lever's weight, and how much tension to apply to a release hook. This knowledge was likely passed down through hands-on apprenticeship, a living blueprint in muscle memory, and refined craft that was lost when that unbroken chain of masters and apprentices was finally broken. The enduring mystery of the seismoscope's interior is a powerful reminder that a blueprint can describe a concept, but it cannot always capture the master's touch, the subtle, unwritten wisdom that turns a good design into a legendary one. A Roman arch was not merely a curved opening, it was a calculated act of defiance against gravity itself. While earlier civilizations used arches, the Romans perfected a specific and revolutionary form, the segmental arch. Unlike a traditional semicircular arch that bulges high, the segmental arch is a flatter, more elegant curve, a shallow arc that spans a wider space with less material. This seemingly small geometric change was an engineering earthquake. It fundamentally altered how weight was channeled downward and outward. The flatter curve created a more efficient line of thrust, directing the immense forces of the structure along a path that minimized sideways pressure on the supporting walls or piers. This single innovation unlocked architectural possibilities that defined an empire. It allowed for the construction of vast aqueducts that strode across valleys on impossibly slender legs, their multiple tiers of flat arches creating a lattice of strength. It enabled bridges with wider, more stable spans that could withstand the torrential floods of seasonal rivers. The true genius, however, was not just in the shape, but in the execution. Roman engineers employed complex mathematical calculations to determine the precise curve and the exact dimensions of the wedge-shaped stones, the voussoirs that formed the arch. Each stone was individually carved to fit its specific place in the compressive puzzle. The entire structure was supported by a temporary wooden frame during construction, but once the central keystone was tapped into place at the apex, the wooden supports could be removed. The arch would then stand entirely through compression, each stone locking its neighbors in a perfect balance of mutual support. This knowledge of stress distribution and the specific construction techniques, passed down through guilds of builders, evaporated during the Middle Ages. Later builders, lacking these precise calculations, often overcompensated with thicker walls and smaller openings, their structures clumsy and inefficient by comparison. Today, modern civil engineers still run computer models on Roman aqueducts and bridges, not as historical curiosities, but as master classes in structural integrity. They are trying to decode the forgotten formulas that gave a 2,000-year-old bridge a lifespan that shames our own modern infrastructure. This architectural blueprint demonstrates that some of the most profound truths of physics were not discovered in a laboratory, but were carved in stone by builders who understood the silent language of force and counterforce. Three brothers in 9th century Baghdad were designing programmable orchestras. The Banu Musa brothers, brilliant scholars in the House of Wisdom, compiled their life's work into the Book of Ingenious Devices, a volume filled with mechanical wonders that sang. Their automated musical instruments were not simple noisemakers, but complex machines capable of performing complete, changeable melodies without a human musician. One of their most stunning creations was an automatic flute player. They designed a mechanical flute that used a steady stream of air from a hydraulic organ, controlled by a rotating cylinder studded with carefully placed pins. As this cylinder turned, the pins would trip levers, opening and closing the flute's finger holes with perfect timing. The result was a machine that could play a precise, pre-composed tune, its wooden fingers moving with a ghostly accuracy. The true breakthrough, however, was in the programmability. The pins on the cylinder were not permanent. They could be removed and repositioned, or the entire cylinder could be swapped for another. This meant the same machine could play an entirely different melody simply by changing its physical programming. A joyful celebration tune could be replaced with a solemn processional in moments, all by rearranging the pattern of pins on a drum. This system of raised pins and empty spaces is a physical binary code, a direct mechanical ancestor of the punch cards that would program the first computers over 1,000 years later. The Banu Musa brothers were not just building musical toys, they were mapping the fundamental concept of a stored program, a sequence of instructions that a machine could execute automatically. Their work proves that the desire for programmable entertainment, for art generated by automated systems, is not a product of the digital age. It was a sophisticated pursuit in the medieval Islamic world, a blueprint for mechanical computation whose melody was silenced for centuries, waiting for the right key to unlock its potential once more. The sheer scale of the challenge is almost incomprehensible. To move a single Egyptian obelisk, a solid granite needle weighing over 300 tons, from its quarry to a temple hundreds of miles away required a logistical miracle. These were not just stones, they were statements of divine power carved from the living earth, and their journey was a masterpiece of practical physics. We have glimpses of the process from tomb paintings and later Roman accounts, but the full blueprint for this ancient heavy lift remains frustratingly incomplete. The first step was to free the monolith from the bedrock. Workers would dig channels around the intended block, then drive wooden wedges into precut slots. These wedges were soaked with water, and as the wood expanded with tremendous force, it would cleanly crack the granite along a perfect line. Once freed, the real puzzle began. How do you move a weight equivalent to 200 cars across sand without crushing wheels or sinking? The solution was a synergy of earth, water, and human rhythm. The obelisk was likely loaded onto a massive wooden sledge, but instead of dragging it raw across the desert, engineers would create a temporary road of lubricated mud. They poured water ahead of the sledge, turning the sand into a slick surface that drastically reduced friction. A team of hundreds, if not thousands, of laborers would then pull on ropes, walking in a coordinated, rhythmic cadence to keep the sledge gliding forward. Some theories suggest they may have even laid down wooden rails, constantly moving them from the back to the front, creating a rolling pathway for the colossal load. The journey to the Nile was only half the battle. For the river voyage, the Egyptians turned to the principle of buoyancy. They would build a special, extra-wide barge with a deep draft. The obelisk was then carefully maneuvered onto this vessel, perhaps by flooding a canal dock to float the sledge directly onto the barge's deck. The sight of this stone mountain floating serenely down the river must have been a powerful testament to the engineer's command over nature. But the final act was the most daring and mysterious of all, the raising ceremony. At the temple site, the obelisk was dragged up a massive earthen ramp built at a steep angle against its intended pedestal. The base of the stone was positioned over the foundation stone, which had a small, carved recess. Then, as a priest likely chanted and a crowd watched in tense silence, crews began the delicate process of removing the sand from beneath the sledge, allowing gravity to slowly pivot the monolith downward. Ropes controlled its descent, guiding the base into its socket until the obelisk stood at a precarious 45-degree angle. The most critical moment came next, pulling it fully upright. This may have been achieved with an elaborate system of ropes and counterweights, or by carefully dismantling the ramp from the top down, allowing the obelisk to settle into a vertical position. The precision required was absolute. A single error in calculation would mean catastrophic collapse and the loss of years of work. This forgotten knowledge of large-scale logistics, of managing friction, fluid dynamics, and human power on a monumental scale, rivals the planning for any modern skyscraper or bridge. It demonstrates that ancient engineers possessed a deep, intuitive grasp of physics that they translated into reality through sheer organizational genius. Their methods may be partially lost, but their silent, standing stones ask us a persistent question. How did they achieve such perfection with such seemingly simple tools? And what could we learn if we could fully decipher their lost manual for moving mountains? Reverse engineering the Antikythera Mechanism has become a journey of rediscovering lost genius. Modern teams, determined to understand its secrets, committed to a radical approach. They would rebuild it using only the tools, materials, and knowledge available to an ancient Greek workshop. This meant forging bronze gears by hand, cutting teeth with files, and assembling everything without the aid of digital calipers or computer models. The process was painstaking, but it revealed engineering subtleties invisible to X-rays alone. The craftsmen who built the original were not just following a plan, they were making constant minute adjustments based on the feel of the metal and the meshing of the gears. One of the most profound discoveries came from analyzing the device's specific gear ratios. The main gear train uses a ratio of 254 teeth to 19. This seems like an odd, clunky number until you realize it perfectly represents the Metonic cycle, a period of 19 years after which the phases of the moon repeat on the same calendar dates. The ancient Greeks knew this astronomical cycle, but to encode it so perfectly into interlocking bronze wheels demonstrates a fusion of mathematical theory and mechanical practice that is staggering. The engineers did not have a calculator, they had an intimate understanding of prime numbers and cyclical patterns, translating celestial harmony into tangible machinery. Another gear with 223 teeth was found to correlate precisely with the Saros cycle, used for predicting eclipses. These ratios were not approximations, they were the most efficient and accurate integers possible for the task, solutions that a modern engineer would arrive at with advanced software. The ancient builders found them through sheer intellectual power and observational rigor. This hands-on reconstruction did more than confirm the mechanism's purpose. It revealed a hidden layer of engineering brilliance. The builders incorporated subtle design choices to handle friction and backlash, the slight play between gears. They understood that a machine made of metal would expand and contract with temperature, and their tolerances accounted for it. The process of rebuilding these forgotten blueprints forces a humbling realization. We are not just recovering lost technology, we are relearning a different way of thinking, a tactile, integrated approach to problem-solving where the line between mathematician, astronomer, and engineer simply did not exist. The true blueprint was not just the gear train, but the sophisticated mind that could see the music of the spheres and build a machine to play it. These 30 blueprints reveal a hidden conversation across millennia. The same timeless principles echo from the Antikythera Mechanism's gears to the self-healing Roman concrete, from Zhang Heng's seismoscope to the Inca's renewable bridges. The most fundamental of these is the elegant application of simple machines. The lever, the pulley, the inclined plane, the screw, and the wheel and axle. These are the basic building blocks of physics. Ancient engineers, lacking our power sources, became masters of combining these elements into astonishingly complex systems. Heron's temple doors used levers and pulleys activated by steam. The south-pointing chariot employed a differential gear, a sophisticated fusion of wheels and axles, to solve a navigational problem. The Roman hypocaust was a masterwork of the inclined plane, channeling hot air with perfect efficiency. These are not primitive tricks, they are the same core components you would find in the hydraulic arm of a modern excavator or the gearbox of a high-performance car. The materials and power have changed, but the underlying physics of force and motion remain constant. Another universal principle is a deep, intuitive understanding of material properties. The makers of Damascus steel did not have electron microscopes, but through generations of trial and observation, they learned to manipulate iron at the nanoscale to create a supermaterial. The builders of Mohenjo-Daro understood how to make clay pipes and bitumen seals that would last for centuries. The Incas knew the precise tensile strength of their grass ropes and how to weave them to bear immense loads. This hands-on material science was a form of embodied knowledge passed from master to apprentice, a wisdom as valuable as any modern data sheet. Then there is the relentless application of mathematical relationships. The Greeks encoded the complex Metonic and Saros astronomical cycles into the precise gear ratios of the Antikythera Mechanism. The Romans calculated the exact curves and compressive forces of their segmental arches. The Maya used a base 20 numerical system and a concept of zero to predict planetary movements with stunning accuracy. They were using math as a predictive tool, a language to describe and anticipate the behavior of the physical world, which is the very essence of modern engineering. What does this recurring pattern tell us? It suggests that the best engineering solutions are often convergent, faced with the same fundamental problems of moving weight, measuring time, or harnessing energy. Brilliant minds separated by centuries and continents will often arrive at startlingly similar answers. The differential gear appeared in both ancient Greece and ancient China. The concept of programmable automation emerged independently in the workshops of Alexandria, the courts of Anatolia, and the halls of Baghdad. This is not a coincidence. It is evidence that the logic of physics and mathematics presents a limited set of elegant solutions. The real difference between then and now is not necessarily the brilliance of the concept, but the context that allows it to flourish. We have better materials, more powerful energy sources, and global communication that prevents knowledge from being so easily lost. But the core principles of innovative problem solving, of observing nature and bending its rules to human will, have always been the engineer's true tools. Recognizing this continuity transforms our view of progress. We are not the first to dream of automated machines or sustainable cities. We are simply the latest participants in a very long conversation, one where we can still learn from voices that have been silent for thousands of years. Their forgotten blueprints are not just historical curiosities, they are timeless lessons in ingenuity, reminding us that the greatest resource in any age is not the technology you hold in your hand, but the creativity of the mind that wields it. This pattern of disappearance is no accident. The most brilliant engineering concept can vanish overnight when the civilization that nurtured it falls. Political collapses were the great erasers of history, wiping out entire libraries of technical knowledge in a single, catastrophic sweep. The legendary Library of Alexandria was not just a building full of scrolls, it was a living network of scholars, engineers, and craftsmen. Its destruction was a permanent brain drain, severing the thread of understanding for countless devices and theories. But even without a dramatic fire, knowledge could simply fade away through the slow fragmentation of an empire, as trade routes disintegrated and the specialized guilds that passed down intricate building techniques dissolved into isolated villages. Sometimes the loss was more deliberate. During periods of upheaval, unconventional ideas were often suppressed as heresy or threats to the established order, their creators silenced and their work destroyed. And then there is the quietest and perhaps most tragic form of forgetting. A blueprint could be so far ahead of its time, so lacking in the contemporary materials or manufacturing power needed to bring it to life, that it was simply filed away as an inventor's beautiful but impossible dream. It was a solution waiting for a problem that the world did not yet feel urgently enough to solve. This specialization of knowledge made it incredibly fragile. The secret of Roman concrete was held by a small class of military engineers. The formula for Greek fire was a state secret known only to the emperor and a handful of chemists. When those few individuals perished or their institutions collapsed, the knowledge died with them. It was not stored in multiple backups or shared across a global network. It existed as a fragile thread, easily snipped. In many cases, the only reason we know about these marvels at all is because a single manuscript survived by chance, tucked away in a monastic library or a private collection, ignored for centuries until a modern scholar recognized the revolutionary ideas hidden within its pages. This recurring cycle of loss and rediscovery forces a humbling realization. Human progress is not a steady, upward climb. It is a fragile flame passed from one age to the next, often guttering in the winds of upheaval only to be rekindled centuries later. Understanding why these blueprints were forgotten is not just an academic exercise, it is a vital lesson for our own time. It teaches us that no technology, no matter how advanced, is permanent. It underscores the profound importance of preserving diverse approaches to problem solving, of sharing knowledge openly across cultures and generations. For every blueprint we have recovered, how many more were lost forever, their secrets waiting to be imagined all over again from scratch? Our journey through these forgotten workshops and shipwrecks leaves us with a profound realization. The spark of genius is not a modern invention. For thousands of years, human minds have consistently pushed against the boundaries of their eras, envisioning futures that their own technology could not yet build. These 30 blueprints are not mere historical curiosities. They are a powerful testament to a timeless ingenuity, a creativity that transcends the specific tools and materials of any given century. We see the same elegant problem solving in the gear trains of the Antikythera Mechanism as we do in the self-healing chemistry of Roman concrete. This recurring pattern shatters the comforting myth of linear progress. Our technological story is not a straight upward climb. It is a spiral where brilliant insights emerge, are lost in the chaos of collapsing empires or fading traditions, and are then independently rediscovered when the world is finally ready. The differential gear appears in ancient Greece and then again in medieval China. Programmable automation is conceived in Alexandria, perfected in Anatolia, and reinvented in Baghdad. This is the convergent logic of physics and mathematics presenting its most elegant solutions to minds separated by continents and centuries. So what does this mean for us, facing our own complex challenges of sustainability and design? These forgotten masters offer more than just inspiration. They provide practical lessons in working with nature, not against it. The Persian Windcatcher shows us how to cool buildings with the wind itself. The Inca bridge teaches the wisdom of renewable systems, of building with an understanding of a material's natural life cycle. The Mayan astronomers, with their deep time calculations, model a patience and foresight we desperately need today. They remind us that the most sophisticated solution is not always the most complex or energy-intensive one. Sometimes it is the one that listens most closely to the world. The next great innovation, the one that solves a critical modern problem, might not be born in a Silicon Valley lab. It could be waiting for us, its blueprint already drawn in the silent stones of an ancient city, or hidden within the pages of a manuscript we have yet to fully understand. Our task is to look backward with as much curiosity as we look forward, to recognize that the seeds of our future were planted long ago, and that human creativity is the most renewable resource we have ever possessed. These forgotten blueprints are not just relics, they are invitations. They ask us to look closer at the world around us and question the simple story of progress we have been told. If these engineering marvels have sparked your curiosity, the journey does not have to end here. You can stand before the intricate gears of a reconstructed Antikythera mechanism in a museum, feeling the weight of its genius. You can scroll through digital archives, tracing the delicate lines of Heron's automatons or Al-Jazari's water clocks in high-resolution scans of ancient manuscripts. For the truly adventurous, you could even attempt a small-scale reconstruction of your own, feeling the same challenges these ancient engineers faced as you try to make a working model from wood, string, or simple gears. This hands-on exploration makes their accomplishments feel even more real, more tangible. I would love to hear which of these blueprints surprised you the most. Was it the self-healing Roman concrete or the programmable orchestras of Baghdad? Share your thoughts in the comments below, and tell me if you know of other forgotten innovations that seem to whisper secrets from the past. If you want to join us for more explorations into history's hidden technological treasures, be sure to subscribe and tap the notification bell. Our next journey into the past's most forward-thinking designs is always just around the corner, waiting to be uncovered.